Rigid bodies, center of mass dynamics. By rigid body, we understand a body that has a fixed shape. Recall that the center of mass we defined as a sum over all of the parts of our body. Let's denote little chunks by index alpha of mass of this chunk times the distance to this chunk, which of course can be written total mass 1 over m, and then volume integral of position and the element of the mass, where the element of the mass itself will be given by the density rho and the element of the volume. For the total momentum of a rigid body, we write that it will be given by the vector sum of individual momenta for each chunk alpha, which is given by the sum of mass alpha times the velocity of the chunk r alpha dot, which from the above definition is equal to the total mass m times the velocity of the center of mass. If we time differentiate this equation again, we will find that m r double dot, the center of mass, will be given by the external force acting on the body. In other words, we get the result that we're already familiar with, that the motion of the center of mass of a rigid body is the same as a motion of a point mass m subject to external force F external. Next, let's consider total angular momentum. Consider the following diagram. Relative to some point O, the center of mass described by vector r, the individual chunk of the body, alpha, with mass m alpha, is given by vector r alpha prime, which gives us the total position r alpha without prime of this chunk. Now the body itself is something like this, with its center of mass given by this point here. So the relationship between the position of the chunk alpha is given by the center of mass r plus the relative position r alpha prime. The angular momentum of chunk alpha around point O is simply the cross product of r alpha cross momentum, linear momentum p alpha, which of course is nothing other than r alpha cross m alpha and then velocity r alpha dot. Next, we write the total angular momentum of a rigid body, which is simply a sum of the angular momenta of all individual chunks, L sub alpha, or the sum of all r alpha cross m alpha r alpha dot. By substituting the expression of each individual chunk with respect to the center of mass, we'll get for the total angular momentum L, we'll get 4 terms, sums. 2 terms for each r sub alpha and 2 terms for each r sub alpha dot. the first term will be the center of mass R cross M alpha R dot center of mass plus the sum of R center of mass cross M alpha R alpha prime dot plus the sum of R alpha dot M alpha R center of mass dot plus the sum of R alpha prime cross M alpha R alpha prime dot. First of all, note that this sum here of M alpha R alpha prime is actually equal to 0, since this is the definition of the center of mass. If we differentiate this expression with respect to time, we're going to get that the sum of M alpha times R alpha prime dot to be also equal to 0. Therefore, we note that the second term gives us 0 because we can factor out R, and likewise the third term is also going to be 0 because here we can factor out R dot, and the sum of M alpha R alpha prime will be 0. Therefore, we get the result that the total angular momentum of a rigid body will be center of mass cross, and here we have total mass m times velocity r dot plus the sum of r alpha prime cross m alpha r alpha prime dot. The first term we recognize as r cross total momentum of the solid body, capital P, and the second term we recognize as the motion relative to the center of mass, because only r-primed quantities appear there. So thus we get that the total angular momentum is broken into two parts. First, we have the angular momentum of the motion of the center of mass, motion of the center of mass itself, as if it were a point particle with mass capital M, plus the second part is the angular momentum of motion relative to the center of mass. Next, let's consider kinetic energy. Total kinetic energy will be simply the sum over all alpha of half mass alpha times velocity alpha squared. Again, we use our expression for r alpha in terms of the center of mass and r prime quantity to find that the velocity squared will be given by the center of mass plus the relative motion velocity r alpha prime dot, all that squared, which gives us three terms: the velocity center of mass squared plus the motion relative to the center of mass squared plus 2r dot times r alpha prime dot. Thus, the kinetic energy will have three sums. There will be the sum of m alpha r, capital R dot squared, plus half of the mass alpha, sum over all alpha, r prime dot squared, plus we'll have r, capital R dot, sum of m alpha times r alpha prime dot. Above we just proved that this sum, the last sum, is in fact equal to 0 because we are considering only the motion relative to the center of mass. And so we get that the full kinetic energy of a rigid body can be decomposed into two parts. Capital M, full mass, times the velocity of the center of mass squared plus the sum of the kinetic energies of the individual chunks m alpha, which we recognize as, of course, the kinetic energy of the motion of the center of mass and the kinetic energy of the motion of rotation. One final remark we want to make is about potential energy. Likewise, we can break the potential energy into two parts, the total potential energy of a rigid body, as potential energy due to some external field, for example, gravity, plus the potential energy due to internal interaction between various parts of the rigid body. However, since the shape stays always fixed, there's no deformation of ideally rigid body, it means that the internal potential energy will always be constant or fixed.